You are welcome to FANOC Research Group YouTube channel. Please click on the subscribe button to subscribe to our
Okay,
YouTube
so
channel. You will get notified whenever new
I'm sure you can see
video
my screen,
is
so we
uploaded.
can
Thank you.
commence. So we'll be doing application. We are rounding up the course already. That's the function analysis class. So we'll be doing application, and one of the popular areas of application of function analysis is optimization. Optimization. Optimization is so large. Optimization is divided into linear optimization and non-linear optimization. Uh, uh, this class, non-linear, most of the tools that you need is basically functional analysis, all those tools we've learned. Of course, linear, there are several linear programming methods, which we call LP methods for solving problems here. So for most of the times, nonlinear optimization has problems that are more difficult to solve than linear. And of course, you know that nature obviously presents a whole lot of problems in nonlinear, dealing with nonlinear case. So that is why um, here, applying function analysis method is always very key. And of course, the problem of optimization is basically finding, of course, when you define a function within a domain of f to range of f. Okay, so the problem of finding a particular number x in the domain of f, okay, such that you have that f of, let me call this f x star, because it's a particular x star, which we call the minimizer. So such that f of x star is equal to minimum, minimum, or because of the domain, let me not use minimum, let me use, because of the domain, it's not, if I'm using intervals, I can talk of minimum. So, but if I use an abstract set like D like this, so I can talk of the infimum. We've already dealt with that. You know what we call the infimum. Infimum, as X varies in D. Remember, we're talking of X star here, but this X is that's why I have to differentiate it. X varies in D of f of x. So this is always the classical problem of optimization. And this method, the methods or the tools we already have in functional analysis will help us to there's a whole lot of theories, that we are going to look at today that gives us the existence of the minimizer. Okay, extra. Okay, so that's the application we'll be looking at today. So let me give you some of the theories in literature that gives us the some conditions under which such a minimizer will exist. These theories are already known in literature. I just mentioned them. But, at the beginning, you see a more difficult conditions, like this theory, more difficult conditions. But researchers has continued to, lessen or weaken the tough conditions like compactness and so on. Okay, so we see a whole lot of those improvements in the conditions. First of all, let's begin with the first set of theories. I call this theorem, if you like, maybe call it theorem 1. Let E be Rn, n-dimensional Euclidean space. Of course, n is a natural number system. Okay, and K, capital K, be a subset of E. Okay, this be compact. Obviously, you can see this is a very hard, this is a very tough condition. Okay, this actually where this theory or this study starts from. So when you see hard conditions like this, mathematicians begin to work on the condition to weaken the compactness assumption. So let f be, a function from K to R. Okay, be continuous. Be continuous. Once again, you know what we mean by a function being continuous. I'm sure you remember. Once again, that's another condition. So then, there exists an X star in K such that f of X star is equal to minimum as X varies in K, f of X. Okay, so you can see what this theory is saying is that if I have E, which is in Rn, E is Rn, and you have K, which is a subset of Rn, okay, this K, a subset of Rn, is compact. Do you know when a set is said to be compact? Any of you? Do you know when a set is said to be compact? I want you to begin to see the difficulty or the the hard condition of this theory. Do you know? Have any of you heard of Ruben Bratu? Have you heard of compactness of a set before? Compactness.
Yeah,
A set is compact where it is close and bounded.
Close and bounded, yeah.
Yeah, what you just said now is a theorem. We call it Hilbert's theorem. A closed and bounded set is compact. That's not definition, but it's a theorem, which is a theorem. I'm sure you know the difference between theorem and definition. So a closed and bounded set, that's what you just said now, is compact. That's correct. That's a theorem, not definition. What I'm looking for is a definition. Anybody? Well, let me go to a set is said to be compact. A set is said to be compact if every open covering, K, we use K now of K, of the set K, for instance, is reducible to finite subcovering that covers it. Reducible to finite subcovering that covers the set K. Okay, so if you can obtain if every open covering of K is reducible to finite, the keyword here is finite subcovering that covers K, that set is said to be compact. Okay, so you say actually constructing those finite subcovering is a difficult task. In practical terms, it's difficult to construct. So that shows you that this condition is a very tough one. Okay, it's a very tough condition. Okay, and of course, even as you go, continuity, yes, not too tough, but we can also get a weaker form of continuity. So you see, mathematicians begin to, once you, yeah, this is the first theory that was obtained, okay, for this type of, for getting a minimizer. But due to the fact that in practice, these conditions are tough, this condition compactness is tough, we begin to think of weakening them. So that's how researchers think. You know, when you have a result that you have some difficulties, you begin to think of how to resolve such difficulty. Okay, as you go delve into research for your PhD and for your master's, that's how you do your research. You see a result, you see a theory. If there's a difficulty in that theory, you might begin to think of how to soften or weaken or remove totally that condition. That's an improvement of that result, and of course it can get published. Okay, but let me find out, Mebratu, Ruben, which area are you researching? Which area in particular are you trying to research? Finance or economics or what?
Yeah, me in finance.
Economics for me.
Okay, economics. Mebratu is MSc or PhD? Which?
It's finance now.
Finance, MSc or PhD?
No, it's my MSc is in financial mathematics. It's
Okay.
mathematics background, so
Okay.
now I'm
Okay. Yeah.
thinking.
It's okay. It's okay. That's fine. So you already have the background. That's fine. So yeah. So as we said, the such trying to weaken such condition of compactness and even continuity, you have the
Oh,
following theory. Yes.
what's covering mean? I don't understand that.
Okay. Open covering. Okay. 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 Let me look at this. Open covering. Now look at this set. Look at this set. A comma B. Yeah, compact. Okay. So this set compact. If you have an open cover for A, an open cover for A, are open intervals. Of course, open covers are open intervals like C, comma D, uh, um, like E, comma F, opening covers like this. If you have something like A uh, plus A plus epsilon, A minus epsilon, sorry, to the left, A minus epsilon, A plus epsilon, okay? So you see that this set will obviously cover A comma B. Okay, a covering is a kind of a set that will contain, okay, the other one. Obviously open the word. That's what open means. It must be open. An open set in R are open intervals like this one. Okay, so if you begin to this epsilon is arbitrary. Okay, so you begin to have A minus epsilon. Maybe if you can begin to call label epsilon 1, epsilon 2, then you have A plus epsilon 2, okay, union A minus epsilon 2, let me not use 2, let me say 3, comma A plus epsilon 4. Okay, if these two union gives you A, comma B. Okay, you now say that these two open sets, covers this one.
Okay.
In other words, if this one is contained in this, so it's finite because you made the union of two sets to obtain this. So that's what we mean by open covering. Open because this set is an open set. This one is also an open set. And the union of these two, if it gives you this, that's finite open covering. Okay, which covers, of course, you know that even open sets like this one, the union of all of these, if you call this AI, BI, I from for I to be 1 to infinity, we cover R. I don't know if you understand what I mean. If you union all the open intervals, you get the whole real line. That's another type of covering, open covering.
Okay.
Do you understand what I mean?
Yeah, I understand.
Okay. Yeah. So, but R is not compact. You know why R is not compact? Even though this one covers R. R is not compact because compactness is it must be finite. The open set must be finite. But if it's finite, it can't give you the whole R. You can't cover R. Okay, because you know that R goes to infinity. R is actually from minus infinity to infinity, is it not? So for you to get up to that, it will be I will be running from 1 to infinity so that you have A1, comma B1, okay, union A2, comma B2, union all of them. A, if you like, because I goes to infinity, A infinity, B infinity, right? Union. So that's the one that will now cover R. This is the one that will cover R. If you remove the infinite condition so that it will be finite, it's not going to be up to R. It's not going to cover R. Okay? So that's why R is not compact, because you cannot reduce this open covering. Yeah, they are open covering quite all right, but you cannot reduce. There's no finite condition such that it will cover R. Yeah, you can do that here, okay, so that it covers R, but you cannot do that for R. Okay, so that's that. I give you the two attempts by researchers to weaken that result that we saw. That result that is very tough and that we saw now. So I give you the two theory. We will prove the theory later, but I just want to show you how our researchers obtained some new results to weaken that those tough assumptions of compactness and even continuity. We give the theory and then we now begin to drop the proof, we'll show the proof later, but we have to go into some rudiments of optimization before we can do the proof. So let me state the following theorem. If I call this theorem 2, let X be a reflexive real Banach space, and F a function that will map X to R union plus infinity, be a convex a real reflexive Banach space. Okay. a reflexive real Banach space, and you have F from X to R union, this be a convex proper lower semi-continuous. So you can see is another term of trying to weaken continuity. Semi-continuous function. Okay. Suppose that you have the limits as norm of x goes to infinity of f of x is equal to plus infinity. Then there exists some x bar in x such that f of x bar is less than or equal to f of x. Okay, I continue here. For all x in the domain of f, the domain of x is capital X. What this is saying is that you have that f of x bar is equal to the infimum as small s varies in capital X, which is the domain of f of x. So that's a minimizer over there. Okay, so you can now see that there's no compactness here now. You now have reflexive Banach space, okay, which you can, there are several examples of such Banach spaces really. And then F, you removed the fact that F is continuous and you reduce it to a weaker one, semi-continuous function. If that is the case, then you can always find a minimizer x bar in x such that the limit as norm of x, all x, okay, in x, norm of x goes to infinity of f of x is equal to infinity, such that f of x is always, this is a minimizer, f of x is always less than or equal to f of x for every x in x. What that is saying that f of x bar is actually your minimizer. So x bar is equal to the infimum as x varies in the domain, which is f of x, domain, which is x, f of x. So this gives you yet another weaker form of that theory. There's yet another one, which I will show you now. That's where you are dealing with kind of intervals also. So let me state yet another theory. We are going to prove these theories later, but we need some rudiment or some introductions of some basic terminologies. What we are trying to do is just to show you some of the most important theories. There are three of them. I've given you number one, number two. Let me have another one. Theorem 3. This one says let x be a reflexive real Banach space, and let K be a closed convex bounded and non-empty subsets of X, let the function f be such that K is mapped to R union plus infinity, be lower, that's a weaker form also of continuity, lower semi-continuous, and convex. All these terminologies we are going to define. Semi-continuous, convexity, we are going to define all of those. Convex, if those are conditions are defined, then there exists a minimizer, let's call it X bar, which is in the domain of F, which is in K. Domain of F is K, such that f of X bar is a minimizer, so it's always going to be less than or equal to f of X for every X in the domain of F. That's for all X in domain of F. It has capital K. Okay, that is what we are saying is that you have that f of X bar is equal to the infimum, that's the minimizer. Infimum as all the small s varies in the domain of F, which is capital K, f of X. Of course, if you are dealing with bounded sets like bounded intervals, you can talk of the minimum as s varies in K, okay, of f of X. Okay, they are all the same. So that's the theory. You can now see the hard condition of compactness is removed. All you require is that X is a reflexive real Banach space, and K, which is a subset of X, a closed convex bounded. Of course, all these ones are easier to obtain. Closed set, bounded set, and then convex set. We've already, at least you know when a set is closed, you know when a set is bounded. Convex, we talk about it here also. So you can see, so it's a mild kind of removing the tough condition of compactness and replacing it with these ones. And then this set is non-empty subset of X. Of course, it has to be non-empty. If it is empty, you cannot even find X bar. You can't find the minimizer. So there will not be anything to discuss. So that's why the domain must contain, at least it must contain the minimizer for any meaningful discussion to hold. So if you have your F to be a function from K to R union plus infinity, if this be lower semi-continuous, I'm sure you recall the first theory we defined talked about continuity, which I said in a way is even a stronger condition. But this one, semi-continuous, lower semi-continuous, is a weaker form of continuity. We are going to define all of those as we go on. So if all these conditions hold, then there exists a X bar, which is the minimizer in K, such that f of X bar is always to the left of all the f of X in K, meaning that f of X is always smaller. Okay, so sorry for that. So we go ahead to look at convex sets. Convex sets. Okay, what do you mean by that definition? Okay, let's X be a real linear space And if you have C, which is a subset of X, the set C is called convex, or is said to be convex if you pick up any 2 points, x1, for example, x1 and x2 in that set C, and a particular scalar T from 0, 1, that segment 0, 1. Okay, we have that Tx1 plus 2 will also be in C. Okay, that's convexity. If you have 2 points from a set, x1 and x2, and then T is an element from 0, 1, 0 and 1 included. Okay, you have that Tx1 plus 1 minus T. Of course, 1 minus T is less than 1. Or it could be 1 if T is 1, because 1 is, and of course, if T is 1, you have only this one that will be left, which is Tx1. Okay. Of course, if T is in 1, if T is 1, you only have Tx1. Okay, which is, so it's also in C. So that's convexity. Let me give you geometry. There are some figures that are convex in nature. What this is saying is that if 2 elements are picked from the set, from a convex set, a straight line joining the 2 of them must also lie completely in the set. That's what this geometry is saying. If any straight line joining those, this is a straight line, 0, 1 is a line segment joining x1 and x2, must also be in the set. So that's the meaning of convexity. And we are going to give some geometries and of sets that are convex and sets that are not convex. Look at this circle, a circle like this one. Sorry, but I know that you know that I'm talking of a circle. A circle is convex because if you pick up any 2 elements, x1 and x2, if you use a straight line to join them, that straight line is completely inside this circle. Okay? A triangle is also convex. A square or a rectangle is also convex because if you pick x1 and x2, you join them, it's also there. Even if you pick them at the boundaries here, x1 and x2, you discover that it will lie completely. This is also this convex set. Convex set. This one is also convex set. This one is another convex set. Because if you pick any 2 points, x1 and x2, you can always draw a straight line. This straight line lies completely inside the shape. Okay, but look at this shape. Convex. Why is it not convex? If I pick x1 here, for example, pick x2 here, if you join them with a straight line, you see that part of this straight line are here, right? If this is C, anything here is not in C, it's outside C. this particular set, you see that for all x1, x2 in C, if you come okay, so let me share my screen. The network is fluctuating. It's okay. So you now see that all of this, you have that if I think the diagram is not, let me, okay. So you see that this circle, triangle, or a square, or a rectangle, but for this one, you see that this one is not convex, because here, if you pick S1, S2, and T in 0, 1, you discover that this line segment Tx1 plus 1 minus Tx2, for this particular case, is not in C. It's not completely in C because you can see this line here is not in C. So if it's not in C. If you can even find one element, which in fact all this from here to here is not in C. So this cannot be in C. But for this case, X, this one is also convex. This one is also convex because you see that for all X1, X2 in C, this C in 0, 1, it follows that Tx1 plus 1 minus Tx2 is in C, for all these cases. All these cases are convex. Okay, why this one is not? Okay, we go straight to some conditions or some other results dealing with convex sets. Okay, let me give this proposition or a result dealing with convex sets. Proposition. Let's see B in X. C is a subset of X. Then C is convex. C is convex. That proposition, you have that if C is in X, then C is convex if and only if for every n in N, and for all the alpha 1, alpha 2, up to alpha n, finite number of them, all of these is in a certain index set. Okay, let's call it lambda n. Okay, such that for all x1, x2, up to xn, all of these are in C. You pick up n number of objects that are in C, then we also have that the summation and their finite number of them 1, 2, 3 up to n. So counting from 1 to n of alpha I, x I, all these summation must be in C, must be a subset of C. Okay, so that's yet a good result, and I'm sure you know that this is if and only if. If and only if. That's a necessary and sufficient condition. So such that you can assume that if C is convex, you can show this. And conversely, if this holds, you can show that C is convex. That's actually the proof. That's the proof for that. Okay. We want to give examples.